Hello everybody, welcome to today's lecture where we are going to review all the fundamentals that we learnt related to material balances till now. So, let us start with this overall review which will give you a perfect clarity on whatever we have discussed, and finally we will perform an example problem which looks at all the fundamentals that we have covered and thereby giving you a full closure for what are material balances and related problems. Let us first start with what is the general material balance equation. So, material balance equations are based on the law of conservation of mass. So, the equation itself is input minus output plus generation minus consumption equals accumulation. So, using this general material balance equation, we have performed calculations for various types of systems. What are the types of material balances that we can write? We can write a total mass balance. Total mass of a system is always conserved, which means mass cannot be created or destroyed, thereby the equation becomes input minus output equals accumulation, because generation and consumption terms are 0 for the total balance. You can also write component balances. Component balances are written for the individual components that are present in the system. Here generation and consumption will be 0 for non-reactive species. In most of our calculations we have been assuming steady state. As I had already justified in the earlier lectures, most chemical and biochemical processes and industrial processes operate under steady state conditions except for states where it is either a startup or shutdown of the process. For this reason, assuming steady state is a reasonable assumption and we can proceed with performing calculations by ignoring the accumulation term. The next major concept with respect to material balances is choosing a basis. How do we choose an appropriate basis? If mass, amount or flow rate is given in the problem, then we will use that as the basis for our calculations. If there are more than one mass or flow rates given, then we will use them collectively as the basis for our calculations. If these values are not given, then we will have to assume a convenient basis. Using a convenient basis will make sure that calculations are simple. We should also make sure that all the data given is converted to one basis. For example, composition of solids and liquids is usually given in terms of mass fractions or mass percentages, whereas composition of gases is given in terms of mole fractions. If such mixed units are given, then we should make sure that they are converted to the same basis so that calculations are simpler. Then the next concept we should look at is what balance do we write? Do we write a mass balance or a mole balance, and for what systems these would be valid? For systems without reactions, it does not matter. Both total mass and total moles are conserved. Mass of individual components and moles of individual components are also conserved. This is because there are no reactions happening and generation and consumption terms are going to 0. Balances which you can write for systems without reactions would be total mass and total mole balance, and similarly for component balances also you can write them in terms of masses and moles. However, if you were to consider systems with reactions, total mass is conserved, but total moles of the system is not conserved. In a reaction only mass will be conserved, the moles of the reactant and the products are not the same. However, mass of individual components and moles of individual components are conserved. So, we can write the following equations. We can write the total mass balance and component mass and mole balances for systems with reactions. When we write component mass and mole balances, we need to understand that these reactive components will have generation and consumption terms which have to be accounted for. When we talk about single unit processes, what are the points we need to remember about some of the common single unit processes? For a splitter, the composition of the feed and the exit streams are the same, which means only one independent balance equation can be written, which is either the total mass balance or one of the component balances, which would eventually be simplified to the total mass balance. For other processes, if the process has n components, then n independent equations can be written. This could be one total mass balance and n minus 1 component balances or n component balances themselves. In case of a filter, we need to understand that the filtrate is the exit liquid which is solid free and contains the soluble components. The filter cake is the solid which has some accompanying liquid. We need to understand that the concentration of the dissolved components in the filtrate and the liquid accompanying the filter cake are the same. This is valid when the dissolved components are not absorbed by the filter cake or other additives such as filter aids which may be used during the filtration process. When we talk about multiple unit processes, the important concept which we need to learn and master is to identify which system to start with. The most accurate way of choosing a system would be to divide the entire process into different subunits and perform the degree of freedom analysis to identify which system has 0 degrees of freedom and start calculations from there. However, this technique is extremely tedious and time consuming. Because of this, there are more efficient and simpler ways to start with. The other efficient ways would be to first either start with the overall system as a single system where we consider this as one unit itself, or we start with the first subunit of the system and start performing calculations, or we can start with the final subunit in the system and start performing the calculations. Amongst these three, where do we start? You usually choose a system where the most information is available for you. If there is a system where you have more information on the flow rates and the composition of the streams that are crossing the system boundary, then that is the system you would want to start with. The chances are that is the system which has 0 degrees of freedom. If a single subunit does not have such a system, then you would make a system which basically is a combination of 2 or more subunits. The overall system which you would choose would be such a combination where if you have 0 degrees of freedom, that is where you would want to start with. So, when we perform these calculations, another important aspect which we need to remember is if we have a stream of interest, then that particular stream has to cross the system boundary. By that what I mean is, if we have to calculate the flow rate or a composition of a particular stream, then the system drawn should not encompass this particular stream. This stream has to cross the system boundary either as an input or as an output. Only when we do this, we will be able to calculate the parameters for that particular stream. Another aspect which we need to remember is, if we have no information about a stream, we do not know either the flow rate or the composition or both of them, and it is not a stream of interest, it is not something we need to calculate, then draw a system in a way that this stream is encompassed by the system, so that we do not have to worry about calculating the flow rates or the composition of something which we do not need. When we talk about reactive processes, there are certain parameters which we need to remember. What quantities are conserved? For reactions, mass is conserved, total mass of the system is conserved, total mass cannot be created or destroyed, which means generation and consumption terms will be 0 when we write the total mass balance equation for a reactive process. When we talk about atoms for each of the element, the same law of conservation applies. The number of atoms of each of the element is conserved. Again here you would have generation and consumption terms going to 0. Mass and moles of individual components are also conserved. Generation and consumption terms have to be calculated for these particular component balances using the stoichiometry or other information that is available in the problem. So, basically you can write either molecular species balances or atomic species balances, and amongst molecular species balances you would have generation and consumption terms for the reactive species, and atomic species balances will not have generation or consumption terms. Another important thing which we need to remember about atomic species balances is, we are writing for each atom. For example, if we have methane taking part in the reaction, 1 mole of methane, 1 molecule of methane would contain 1 atom of carbon and 4 atoms of hydrogen. So, even if you have 1 mole of methane coming into the reaction, you would account for 4 moles of hydrogen atom entering into the reaction. So, this is important when we perform atomic species balances. Hydrogen balance for the example I just mentioned would be 4 times the number of moles of methane entering. So, similar principles have to be applied for all the components which are taking part in the reaction. When we talk about combustion reactions, what we need to remember is this is a reaction where a substance reacts with oxygen to form carbon dioxide, carbon monoxide, water vapor and sulfur dioxide and so on. In complete combustion you would have carbon dioxide, sulfur dioxide and water vapor being formed, and in partial combustion you would have some amount of carbon monoxide also being formed. In most of the combustion reactions we can assume that air is 79% nitrogen and 21% oxygen for ease of calculations. So, for such air the average molecular weight would be roughly 29 grams per mole. Nitrogen is treated as a non-reacting component in combustion reactions and in most reactions for that matter. Nitrogen forming NOx is usually ignored while we perform these calculations. This is because this is usually very small and can be negligible, therefore we can ignore it. We need to remember the distinction between what is the wet basis and dry basis. Just as a refresher, wet basis would account for the water vapor component present in the gases also, whereas dry basis will not account for the water vapor present in the gases. So, if you have 10 moles of carbon dioxide, 10 moles of water vapor and 10 moles of carbon monoxide in a flue gas, then in dry basis carbon dioxide mole fraction would be 0.5 and carbon monoxide mole fraction would be 0.5. In wet basis carbon dioxide and carbon monoxide and water vapor would all have mole fractions of 0.33. So, this is what wet and dry bases are. When information is given we need to use them appropriately. When we come to biochemical reactions, these are the following points we need to remember. Michaelis-Menten equation is a mechanistic model describing enzyme kinetics. You can have Monod's equation as the unstructured non-segregated model for growth kinetics. Although we did not describe or discuss how to derive Michaelis-Menten equation, I had mentioned earlier that it can be derived using the enzyme reaction. That is why it is a mechanistic model. Monod's equation cannot be derived. It is more of an empirical model based on unstructured non-segregated modeling which makes certain assumptions. So, we talked about an ideal CSTR or a chemostat when we talked about biochemical reactions. These are reactors where the contents are well mixed. So, what I mean by that is the concentration of all the components are the same at any part of the reactor. Concentration in the exit stream is the same as the concentration inside the reactor. Other points about the biochemical reaction would involve what growth rate and specific growth rate are. Growth rate is an extensive property and specific growth rate is an intensive property which is obtained from growth rate by dividing growth rate with either the biomass concentration or the biomass number. Assumptions which are used in Monod's model are: cells can be represented as a single entity, cells are uniformly distributed in the culture, and cell substrate is growth rate limited process. When we talked about recycle, bypass and purge, there are certain concepts which we need to remember. At steady state, material circulation happens without accumulation during recycle or bypass. What I mean by this is accumulation will be 0 for any subsystem which is studied within the overall system. Recycle with reactions can have two types of conversions: overall conversion and the single pass conversion. Overall conversion is basically the conversion which would happen for the overall system, which includes the recycle stream, whereas single pass conversion is what happens when the reactants pass through the reactor only once. Bypass is a process where you have a stream skipping one or more of the stages to go directly into the downstream stage, and purge is a process where some components are being removed so that you can avoid accumulation of inerts or other unwanted materials which might build up due to recycle. With this we have covered all the basics which we have talked about till now. We will solve two example problems. for getting the overall picture of whatever we discussed. The first example will talk about a chemical system where chemical reactions are taking place and you would have a multi-unit system with recycle and purge. The second system, which is the second example, will talk about a biochemical reaction. In today's lecture, we will perform one example problem and the second example problem will be done in the next lecture.